and general relativity. And the situation with these is they don't overturn Newton's laws, they extend them. It turns out that in the kinds of situations that Newton was looking at, both quantum mechanics and general relativity reduce down to Newton's laws. So you have a situation where here are Newton's laws, N's laws, of which Kepler's laws are a tiny subset. And then general relativity, I'm drawing a kind of Venn diagram here, is here. Relativity, occupying Newton's laws, but then some other stuff. Quantum mechanics looks kind of like this. Extends in a different direction. Let me make these axes specific. I don't like Venn diagrams when they don't tell you what you're actually plotting. This is mass, so heavy things are when relativity kicks in. This is size, and so small things are when quantum mechanics kicks in. But you can see the problem. We've got two big theories. You really want those theories to be encompassed by one yet bigger theory. And that is the current goal of theoretical physics, to try and find the one great theory that encompasses both quantum mechanics and general relativity, which contradict each other in various awkward ways, particularly in this region up here. This is called the theory of everything, or TOE. And the best current guess as to what kind of a theory that will be is that it will be some kind of string theory. I won't go into string theories now. It's big. You can go read many popular books on this. It's very exciting. There is currently no string theory that really works out all that well, but the people who are studying this kind of thing like to believe that that's going to work out sometime in the future. Okay, this is good. We've gone in about 40 minutes from the start of science to the theory of everything. So we're done. Everything else is a detail. And so the whole rest of the course is filling in details. The first of which, so let's start on the details. The first of which, I want to go back and catch one of Kepler's laws. And I want to write down the Newtonian modification of Kepler's third law. And that is an equation that looks like this. A cubed is equal to gmp squared over 4 pi squared. All right, we're going to circle this in red. This is something you're going to want to memorize. It turns out to be a basis of a large fraction of what we're going to do in this course. So let me explain the symbols. A is the semi-major axis, of an elliptical orbit. Remember, these orbits are going to be ellipses. Here's an ellipse. The long side is the major axis. The short side is the minor axis. Half the major axis is the semi-major axis. So this is A right here. P is the orbital period. How long it takes the planet or whatever orbiting object you've got to go around one orbit. M is the total mass of the two things in orbit around each other, of the orbiting bodies. And the existence of that m is why this is Newton's modification. In Kepler's law, it was always planets going around the sun, so the mass was always the same. The mass was that of the sun, and so it canceled out. But in general, you can use the same equation to deal with things orbiting the Earth or things orbiting the Moon, as long as you put in the right mass there. G is a constant of nature, the gravitational constant. And it equals some value depending on what units you use. And we'll come back to that later. 4 is 4. Pi is this obscure number from elementary mathematics, 3.14159, whatever the heck it is. And you can punch it in on your calculator or whatever. So you can use this equation to find things out. Now, these numbers tend to be awkward to work with. The mass of the sun is some huge number of kilograms. G is a very awkward number. Pi is always a mess. But let me show you a trick. Consider the Earth's orbit around the sun. Around sun.